Advanced GraphRAG and Knowledge Agents. Module 7, let's dig in. Welcome back. Module 7 is a double feature, so grab some popcorn. We meet two very different troublemakers. AGRAG fixes how we build the graph and how we walk it, treating retrieval as an optimization problem. StructRAG does something almost philosophical. It rebuilds your messy text into the exact shape your question needs on the fly. Different ideas, same goal, squeeze more reasoning out of scattered knowledge. A quick recap of the road so far. We built relationship-rich graphs, learned to search them, made them cheaper and more memory-like, then went relation-free with linear RAG. Two ideas from that journey come back today, so keep them warm, personalized PageRank from Module 5, and the cost of letting a language model extract everything from Module 2. We will lean on both, not re-explain them. Let's start with AGRAG, Advanced Graph-Based Retrieval Augmented Generation. It published at a top database conference, and the database people fingerprints are all over it. AGRAG looks at GraphRAG and asks two pointed questions. Are we building the graph with the wrong tool? And are we walking it in the wrong shape? Its answers are surprisingly elegant. Here is the pain point. As we covered in Module 2, using a language model to extract entities is powerful but risky. It hallucinates entities that were never in the text, and one bad node early on propagates downstream, poisoning everything connected to it. It also costs real tokens on every chunk. AGRAG's first move is to refuse to pay that bill at all. So AGRAG swaps the language model for a humble, decades-old statistic, TF-IDF. Instead of asking a model what the entities are, it scores which words actually matter in each passage by counting them. Frequent here but rare across the corpus means important. It is non-parametric. Nothing is learned, nothing is guessed, so nothing can be hallucinated. Watch the keywords surface from raw counting. Let's make that precise because the math is beautifully simple. The TF-IDF weight of a term is its term frequency in this document, multiplied by its inverse document frequency across the whole corpus. And inverse document frequency is just the log of the total number of documents divided by how many contain the term. Rare words get a big log, ubiquitous words get nearly zero. No model, no hallucination, just counting and a logarithm. If this feels familiar, good. Back in Module 6, linear RAG also refused to spend language model tokens at construction time, leaning on lightweight local tools. AGRAG shares that instinct. Skip the expensive model when cheap statistics will do, but it spends its cleverness somewhere completely different, not on building the graph, but on how it walks the graph. Which brings us to the headline idea. Here's AGRAG's big idea in plain English. Most graph retrieval walks outward from seed nodes and hopes it grabs the right neighborhood. AGRAG instead poses a crisp optimization problem. Out of this whole messy graph, find me the single best little subgraph, the one packed with relevant, influential facts and almost no junk. Retrieval stops being a walk and becomes a search for the optimal substructure. AGRAG gives this optimization a name, the minimum cost maximum influence problem, or MCMI. Two forces pull against each other. Minimum cost means only include connections that are cheap, where cheap means highly relevant to the query. Maximum influence means prefer nodes that are genuinely important in the graph. The best subgraph is the sweet spot, maximally influential, minimally noisy. Let's unpack the two halves. First, edge cost. AGRAG defines the cost of including an edge as 1 minus its semantic similarity to the query. So an edge whose facts are highly relevant to what you asked is nearly free, while an off-topic edge is expensive. Because we are minimizing total cost, the optimizer is naturally pulled toward edges the query actually cares about. Relevance becomes cheapness. Second, node influence. How important is a node really? AGRAG measures it with personalized PageRank, and yes, this is exactly the personalized PageRank we derived back in Module 5 with Hippo-RAG. Same query-seeded random surfer, same steady-state importance scores. If you want the equation again, pause and revisit Module 5. Here we simply reuse it as the influence signal that MCMI wants to maximize. Now we can write the whole objective in one breath. AGRAG searches for the subgraph that maximizes the total personalized page rank influence of its nodes, while minimizing the total cost of its edges. And remember, edge cost is 1 minus query similarity. Maximize influence, minimize cost. It's a prize-collecting kind of problem. Every influential node is a prize you want. Every noisy edge is a toll you'd rather not pay. There's a catch, there always is. Finding the truly optimal subgraph is NP hard. The number of possible subgraphs explodes combinatorially, so you cannot check them all before the heat death of the universe. That means AGRAG cannot solve MCMI exactly. Instead, like every good engineer facing an intractable problem, it reaches for a greedy approximation that gets you a very good subgraph fast. Here is the greedy idea in motion. Start from the query's most relevant seed nodes. Then repeatedly add the single edge that gives you the best deal, the most influence for the least cost. Each step grabs the locally best bargain. The subgraph grows outward, always chasing value per cost, until adding more would just bring noise. No exhaustive search, just a chain of smart, cheap decisions. Now the clever twist. Earlier graph retrieval methods often build a tree, clean, but trees forbid loops, and real reasoning sometimes circles back. AGRAG lets its subgraph contain cycles and loops. 3 facts that mutually reinforce each other can form a triangle, strengthening the evidence instead of being artificially cut. It just penalizes any connection that looks noisy, so the loops it keeps are the ones that genuinely add information. Let's place AGRAG on the map. Like Hippo-RAG, it uses personalized page rank for importance. Like linear RAG, it skips language model extraction at build time. But unlike both, it frames retrieval as an explicit cost versus influence optimization and embraces cyclic subgraphs. It's the optimization-minded cousin in the family, a database researchers take on graph retrieval. Before we touch any code, let's meet the toolkit, because we never step into a library cold. The reference implementation lives at the GitHub repo wib0627/agrag. It's the official code from the paper. You install it the usual way with pip install -r requirements.txt, and it expects a language model only for the final answer, served through a fast endpoint like VLLM, not for building the graph. The repo is driven by command line flags, and a few of them map straight onto everything we just learned. Edge weighting set to TF-IDF turns on our non-parametric weighting. Steiner tree switches on the subgraph constructor that solves MCMI. There's a retrieval mode, an NER threshold, and an include passage nodes flag. That last one borrows Hippo-RAG 2 passage nodes, which we met in Module 5. The flags are the API, let's see them in action. Now the code, and it's mostly one command because the heavy lifting is inside the flags we just introduced. We point AGRAG at the GraphRAG-Bench novel subset, turn on hybrid retrieval and TF-IDF edge weighting, switch on the Steiner subgraph constructor, include passage nodes, and hand it a VLLM endpoint for the final answer. Under the hood, TF-IDF builds the graph, MCMI greedily carves the best cyclic subgraph, the model answers from it. Build optimize answer 1 pipeline. Does all this optimization pay off? On knowledge-intensive question answering across GraphRAG-Bench's novel and medical sets, plus classification corpora like Web of Science and Reuters, AGRAG edges out strong baselines, including Hippo-RAG 2 from Module 5, Light RAG from Module 4, and even StructRAG, our second act today. The lesson, cheap statistical extraction plus a smarter cyclic subgraph, can beat fancier, pricier pipelines. Let's bank AGRAG before we switch gears. Build the graph with TF-IDF, not a language model, so nothing is hallucinated. Score node importance with personalized page rank from Module 5. Define edge cost as 1 minus similarity to the query. Then greedily carve out the minimum cost, maximum influence subgraph, cycles welcome, noise penalized. Optimization, not wandering. Now let's meet a framework that doesn't optimize the graph at all, it reshapes your knowledge. On to StructRAG, and the vibe is completely different. AGRAG was a database researcher optimizing a graph. StructRAG is a cognitive scientist asking, how do humans actually reason over a pile of documents? The answer is that we don't reason over raw text, we reorganize it. And StructRAG turns that human habit into an algorithm. Think about how you tackle a hard question buried in many documents. To compare prices, you sketch a table. To trace a chain of events, you draw a timeline or a graph. To plan, you write steps. Cognitive scientists call this structure fit. We instinctively convert raw information into the structure that best fits the task. Flat text is where reasoning goes to struggle. Structure is where it gets easy. Standard RAG, all the way back to Module 1, retrieves flat chunks and dumps them into the context window. But when the answer is badly scattered across many documents, a fact here, a number there, a date 3 files away, flat chunks keep it scattered. The model has to do the reorganizing in its head mid-answer, and it often drops the ball. StructRAG's bet do the reorganizing first. StructRAG has 3 stages, and the whole framework is just these 3 boxes in a row. First, a router decides which structure best fits your question. Second, a structurizer rebuilds the retrieved text into that structure, right now at inference time. Third, a utilizer reads the answer off that clean scaffold. Route, structurize, utilize. Let's watch a question flow through all 3. Stage 1 is the router, the brain of the operation. It reads your question and the gist of the documents, then picks the single best structure to use. It's called hybrid because it chooses among several structure types rather than forcing everything into one mold. Pick a table for a comparison, a graph for a reasoning chain. Get this choice right and the rest of the pipeline almost works itself. The router chooses from 5 shapes, each suited to a kind of task. A table for statistical and comparison questions. A graph for long-chain multi-hop reasoning. An algorithm, a list of steps, for planning. A catalog, an indexed outline for summarizing. And plain chunks as the fallback for simple single-hop facts where structure would be overkill. The right shape depends entirely on the question. How does the router learn good taste in structures? Through a training technique called DPO, Direct Preference Optimization. This is new to our course, so here's the plain English version. Classic alignment uses a separate reward model and reinforcement learning, which is fiddly. DPO skips the reward model entirely, you just show the model pairs of outputs, a preferred one and a worse one, and it directly tunes itself to favor the preferred. Simpler, stabler, very popular. So for the router, a preference pair is simply, for this question, structure A gave a better answer than structure B. Feed thousands of those pairs to DPO, and the router learns which structure to pick before it has ever seen your specific query. The obvious question is, where do all those preference pairs come from? StructRAG has a clever, fully automatic recipe. That's the next slide. StructRAG builds its preference data with a 3-step loop and 0 human labelers. Synthesize, a language model invents lots of diverse practice tasks. Simulate, for each task, it actually solves the problem using every candidate structure, once with a table, once with a graph, and so on. Judge, another model compares the solutions and crowns a winner. The winner versus loser becomes one preference pair. Run it at scale and you have a training set for free. Once the router has picked a shape, stage 2, the scattered knowledge structurizer does the actual reshaping. It takes the retrieved raw text and reconstructs it into the chosen format, live at inference time. If the router chose a table, the structurizer reads the messy passages and fills in the rows and columns. The scattered facts get gathered into one clean, queryable scaffold, built fresh for this exact question. This is the phrase in the module title earning its keep, inference-time structuring. Notice StructRAG does not pre-build one giant fixed index like Microsoft GraphRAG in Module 3. It waits until it sees your question, then constructs exactly the structure that question needs and throws it away after. Bespoke structure per query. The trade-off is obvious: flexibility and precision paid for with extra work at answer time. Stage 3 is the structured knowledge utilizer, the payoff. Faced with a complex question, it first decomposes it into smaller sub-questions. Then it reads each answer directly off the structured scaffold, a cell in the table, a path in the graph, instead of squinting at raw chunks. Finally, it fuses the sub-answers into one response. Because the knowledge is already organized, the model's job shrinks from reasoning plus searching to mostly just reading. Here's a neat bonus when the chosen structure is a table. The utilizer can translate your natural language questions straight into a SQL query and run it against the table it just built. Want the average, the max, the count? Don't make the language model eyeball rows and hope. Let a database do exact arithmetic. It's the database researcher and the cognitive scientist shaking hands. Before any pseudocode, let's name the three interfaces, because we introduce tools before we call them. Conceptually, StructRAG exposes a router object, a structurizer object, and a utilizer object, exactly the three stages. The router has a route method, question and document gist in, a structure type out. It's the trained DPO policy we just discussed, wearing a simple function signature. The other two are just as tidy. The structurizer has a structurize method, the retrieve text plus the chosen structure type in, a populated structured object out, your filled table or graph. The utilizer has a utilize method, that structured object plus the original question in, the final answer out, doing the decompose lookup fuse dance inside. 3 methods, 1 clean chain. Now we can read the code without surprises. Now the pipeline is code, and it reads exactly like the 3 boxes we drew. Retrieve the candidate text as usual. Call router.route to pick the structure for this question. Call structurizer.structurize to rebuild the text into that shape. Call utilizer.utilize to decompose the question and read the answer off the scaffold. 4 lines that mirror route, structurize, utilize. No magic, no cold opens because we introduced every object first. The results are striking and they tell a story. On the Loom benchmark for long context, knowledge-intensive reasoning, StructRAG scores around 60, versus the height 20s for a plain long context baseline on the toughest document sets. And here's the pattern that matters most: the harder and more scattered the task, the bigger StructRAG's lead. Structure helps exactly when flat text hurts most. One quick glimpse over the horizon. StructRAG picks from 5 fixed structures, but a follow-up line of work asks, why not let the model invent its own task-specific schema? Using reinforcement learning, methods like StructRAR1 maximize information density, packing the most meaning into the least text. We won't go deep here, just know the field is moving from choosing a structure to designing one. File it under further readings. Let's put our 2 stars side by side. AGRAG keeps the graph but optimizes which substructure to retrieve, a minimum cost, maximum influence subgraph built cheaply with TF-IDF. StructRAG often abandons the graph entirely and rebuilds your knowledge into whatever shape the question wants. Add inference time. One optimizes traversal, the other reimagines representation. 2 answers to the same complaint: scattered knowledge is hard to reason over. So which do you grab? Reach for AGRAG when you already have a graph and want sharper, cheaper, cycle-aware retrieval over it without paying for language model extraction. Reach for StructRAG when your answers are scattered across many documents and the real bottleneck is representation, when a table or a timeline would make the question trivial. And honestly, nothing stops a production system from borrowing the best of both. Let's lock it all in. AGRAG build with TF-IDF, not a model. Reuse Module 5's personalized page rank for influence. Define edge cost as 1 minus similarity. Greedily carve the minimum cost, maximum influence subgraph, cycles allowed. StructRAG, route to the best structure with a DPO-trained router. Structurize the retrieved text at inference time, then utilize the scaffold to read off answers. Optimization meets cognition. That's Module 7. That wraps the research tour. In Module 8, the grand finale, we leave the lab and step into production, AWS's 3-tier GraphRAG toolkit on Neptune and OpenSearch, Llama index workflows that write and self-correct their own cipher against Neo4j, and GraphRAG-Bench to measure it all. Everything we've learned assembled into real multi-agent systems. I'll see you there for the big one.
If you like this video, please subscribe and share. Thank you.